back to theory. Okay, so that's where we are today, right? So this is a branch of combinatorics. How do you spell likelihood? Like that?
No.
No, there's no Y.
Mutual.
E-L?
Yeah.
Double R on occurring? Or single? You guys say double? Okay. So, probability is a branch of, don't worry about it. We'll let the English teachers and the spell checkers deal with that later. Okay? So probability is a branch of combinatorics. And probability calculates chance or likelihood of an event occurring. In other words, if you buy one lottery ticket and your probability of winning the lottery is X, right? You buy 2 lottery tickets, what's your probability of winning the lottery? 2X, right? So, we all have an intuitive understanding of what that is, which is important, because that intuition coupled with the theory that you'll learn today is what will guide you through difficult situations. Now, let's give it a more formal definition, and I think knowing me, I probably gave you a definition of it earlier in the year because I don't like those combinatorics questions on visually distinguishable or indistinguishable cases because they screw things up for probability. Who remembers me vaguely talking about that? So who remembers me giving a definition for probability earlier in the year?
I think you did.
Probably did, but it doesn't matter because we're going to give it again. Okay. So probability. So the probability of an event occurring. See, when you write faster, the spelling comes to you easier. I didn't have to think that. The probability of an event occurring equals the total number of equally likely, physically possible ways that event can occur. 2 R's after occur? No. Because the English is divided by the total number of equally likely physically possible ways, all possible events or outcomes can occur under the problem's constraints. So some of you will probably look at this and say, this is a load of crap. Like, how many words can you write, Mr. Segev? And some of you may actually look at this and say, I understand why he's writing all of these words and why he's underlining where he's underlining. And some of you may be like, I have no clue either way, but I'm sure I'll find out, or I hope to find out. But I'm actually choosing my words pretty carefully. Let me see what I wrote here. Probability of an event occurring equals the total number of equally likely, physically possible ways that event, I could even write that desired, if I want, that desired event can occur, divided by the total number of equally likely, physically possible ways all possible events or outcomes can occur under the problem's constraints. Let's examine things. What do I mean by under the problem's constraints? What do you think I mean by that? For example, let's say I'm talking about the probability of drawing 3 cards from a standard deck of 52 cards and having them all come up diamonds, right? Is one of the possible events to have 4 clubs? No, because one of the constraints I introduced was that you are drawing 3 cards. So your denominator for probability isn't the universe of everything. It's only the universe governed by the constraints of the problem. Can I get a show of hands of those of you who understood what I just talked about? That's good. What do you think I mean by equally likely, physically possible?
Not visual, this like. Not that. Not visual distinguishable.
Okay, yeah.
Like,
sort of, yeah.
Like the 2 objects.
Yeah.
The 2 objects can be the same.
Well, actually, they're not the same.
Yeah, they can't be the same.
I think I know what you're saying, but I'm not sure. Yeah.
Like you close your eyes and then you randomly pick one thing, the possibility is the same.
Okay, that's the equally likely part. That's good. So that every event you're talking about is just as likely to happen. So if you're talking about choosing an object, right? The mechanism or method by which you choose that object, let's say it's object A, has to be the same mechanism or method by which you choose any other object. Otherwise, things will be tilted, right? Like let's say you have a jar with a red marble and a green marble in it, right? And let's say the jar is filled with other things, right? And all things being the same, the probability of choosing the red marble should be the same as the probability of choosing the blue marble if they're the same size and shape and so on and so forth, right? Well, that also assumes that when you go in, you spend just as much time going in to grab a blue marble as you do for a red marble, right? It's not that if you go for a red marble, you can't, if you want things to be according to this definition, you can't spend 5 hours looking for the red one, right? And then only go in and try and grab the green one quickly, because obviously then the probabilities are not going to be 50-50, right? The mechanism where you spend less time is going to yield a lower probability. So that's what we mean by equally likely, okay? Now, physically possible has to do with what Milad was talking about. And that's this idea that just because things look identical has no bearing on probability. Because even though you have 2 green marbles that look the same to you, they are still 2 physically distinct marbles. And probability is all about that. Okay? So for example, if I have a bag of 3 green marbles and 1 black marble, if I keep on, and I'm taking out, let's say my objective is to pull out 3 green marbles, right? Before probability, it wouldn't matter how many green marbles you had. As long as you had at least 3, there was only one way to grab 3 green marbles, right? Because they all look the same. But in probability, if you have 3 green marbles versus 10 green marbles, is there a difference in likelihood of pulling out 3 green marbles?
Yeah, like it's lower, the chance to get a green marble than a black.
Say that again?
Like the chance to grab a green marble is lower than to grab a black marble.
If you have in scenario 1, 3 green, let's say 1 black, right? And scenario 2, you have 1 black and you have, and let's say you have 5 green. What is your likelihood, where is your likelihood higher of grabbing 3 green? Scenario 1 or scenario 2?
Scenario 2.
When it comes to visually distinguishable, if you're grabbing 3 objects that are the same, you only have one option, 3 green, right? There's only one way you can do it. But in probability, it's not about that, because in probability, in this case, how many ways can you get 3 green? One way. How many ways can you get 3 green here?
Of,
5 choose 3.
5 choose 3 if you don't care about the order, if you took them all at once. And if you care about the order in which you took them, 5, no, 5P3, right? Doesn't matter, we're not there yet. Doesn't matter. Do you guys understand that? You understand that? So in actuality, when it comes to probability, you can think of this as G1, G2, G3, G4, G5, because they are physically different objects. Okay? How many of you guys follow what I was talking about over here? Okay. Now, we can talk about scenarios whereby we physically choose the objects, let's say, from a bunch of objects one by one, or if we're taking multiple objects, we just choose them all at the same time, in which order doesn't matter. And we can see if those 2 different scenarios have any bearing on probability. Okay? Now, what do we got here? 1, 2, 3, 4 green. Right? And we have 2 brown, or gold, peach, whatever, peach. 2 peach, and we have 1 blue. 4, 2, 1. So we have theoretical probability, and we have experimental or empirical probability. All right? Okay. Wait a minute. No, wait. We can pause this. We've got to do the lates. We have theoretical probability, and we have empirical or experimental probability. What do you guys think the difference is? Put up your hand. What do you think the difference is?
Experimental, is it empirical?
Empirical or experimental, these mean the same
I think
thing.
it's like once you actually do it,
Yeah.
so and then theoretical is on paper. Like,
Yeah.
kind of.
Theoretical is when you do the calculation on paper using combinatorics, and empirical information is information that you see from the taking place of an event, okay, or a simulation or an experiment. Okay, so I could ask you guys a question. First, we could do, and then let's do some theoretical calcs. Let event A be defined as drawing 3, should we do 2? Doesn't matter. 2, what are those? Candies? Could take a while. Sorry. Calculate BA I just don't want to waste too much time. That's okay. If two candies are randomly drawn one after the other. Actually, no, I'm going to do this. I'm going to take A off of there. I'm going to calculate PA if two candies are randomly drawn, A, one after the other, B, simultaneously.
Simultaneous.
That means at the same time. So why don't you guys do that? You want me to read it?
Yes.
It's a little short on chalk. It's getting messier and messier. Okay. Theoretical calculations. Number one, let event A be defined as drawing two candies from a box. And we'll say randomly. Randomly drawing two candies from a box. What does randomly mean?
You have the same chance.
Do you look out, do you seek out a color or a candy? No. Let event A be defined as randomly drawing two candies from a box and having them both be green. Calculate the probability of event A if two candies are randomly drawn, A, one after the other, B, simultaneously. So in one experiment you go, candy 1, register color, candy 2, register color. Experiment 2, you just grab a couple at the same time and you register the colors. Okay? So what you guys are going to do before we actually carry out the experiment is you're going to calculate both of those. And we'll take that up in a couple minutes. Can I erase over here? It'd be nice to have this definition up here. You know what, I'm going to leave this definition up here, and I'm going to take out all of this and carve ourselves a little niche.
So there are 8 candies there?
What do we got? 4, 6, 7. 4, 6, 7. 4, you see them here? 4 green,
Oh, okay.
2 peach, 1 blue. And I will recreate that in this box. Hopefully Ms. Bernanke doesn't see this and doesn't kill me. 1, 2, 3, 4. It was 4 green, right? 4 green. I'll move 2 blue.
No, one blue.
Shoot. That would have ended it right there. Now what we do need is we need a projector, and that's what we really need. No, we don't. We're going one at a time. So we're just going to need to keep a running total. Ideally, we would have had multiple bags and multiple, whatever. We'll get it done.
Sir,
Yeah.
experimental and
Yeah. You talk about empirical information. So for example, let's say you're manufacturing a product, right? For example, from experience. Let's say you're manufacturing glass and you want to temper the glass, affect its strength. Maybe you have some theoretical ideas about how to operate the process to make it a certain strength, but you're not sure. But let's say you've been running this facility for 100 years. Probably some of the people that don't have the theoretical knowledge have been doing it long enough, such that maybe they can't tell you exactly why they get the glass to be that specification, but they know the recipe to follow. Why? Because they have done it by trial and error long enough. So in the case of this problem, some of you may have an idea as to how to figure out the answer before actually trying this physical experiment. But the empirical data is actually trying the physical experiment and recording what happens. And what is always the correct answer? The empirical or the theoretical?
Empirical.
Empirical is always the correct answer. Always. The experiment is always true, assuming that you didn't screw things up. Okay? The experiment is always true. If the theoretical doesn't agree with the empirical, you did something wrong with the theory, not the reverse. That's the scientific method. Unless there's been an experimental flaw, in which case you have to have that experiment run multiple times, maybe by different folks, okay? Peer review the methods. But with regards to a simple experiment like this, I don't think we have much of an issue. Okay? Yeah.
What's the difference between one after the other or simultaneously? Because when you're doing it simultaneously, are you still grabbing one after another, like back?
Well, we'll see. I like the thinking. Assume that in some utopian way you could literally grab them at the exact same time. Okay, who has answers? 1 to P versus 2 versus. So we'll wait. Did we mark absences or not yet? Okay. Did we mark absences too or no? That's what we did. Rohan. Rohan, are you here? No. Micah, yes. Nikita, are you here? No. Janice, yes. June, Jami, Tony. Krish, Brijesh, Preet. Preet? Preet is not here.
So can I go closer now?
Yes. Darwin, Aaron, Alexei, Naomi. Okay. So, okay, so let's go over this. So, I told you that by definition, I should even write this down. So in A, it's drawing 2 candies, one after the other. Randomly drawing 2 candies, one after other. And getting 2 green. Is that right? So what we write is the probability of the successful event. I've decided to call it A. You can call it anything you want. You literally could have called it probability of 2G if you wanted, right? Doesn't really matter. You can call this anything you want. But very often I like to create a let statement for what it is and then give it a letter. But it doesn't matter. It doesn't matter. So we can call it probability of 2 green, call it probability of A. I said that's going to be the number of equally likely physically possible ways you can achieve the success, which is going to be the number of ways you can achieve event A, divided by the total number of physically possible equally likely ways the event can turn out. And we like to use the letter S, as you remember, right? For the universe of possibility, right? So let's talk about the numerator. In this particular case, we're talking about drawing 2 cards, one after the other, and getting them both green, okay? So in this case, I have 4 green, agreed? And it's basically like taking 4 folks and finding out how many ways, how many 2-person lineups you can create with them, right? 4, P2, agreed? Or if you wanted, you could have said 4, choose 2, and then injected order and gone 2 factorial, right? That's the same thing. Now, again, how many of you said it was one way? Good. It's not one way. Even though they look the same, it doesn't matter. It's about 4 objects, right? And there are 4p2 physically possible ways you can grab any 2 of those 4. That's the total number of physically possible ways you can grab 2 of those 4 objects, which will give you success, which is defined as both of them being green. Show of hands of those who follow that. We know? Oh yeah, pretty good? Now you've got to divide that by the total number of ways that this experiment can happen under the constraints. And the constraint is that you're grabbing 2 things randomly. So you have a total of 7 objects.
So 7 people.
7p2. Okay? And what does that come out to as a decimal or a percentage? Yes?
Question?
That's not an answer. I want an answer first.
Answer, let me have a
Give me
0.286.
0.286. What's after the 6?
Oh, then 0.2857.
Oh, okay. So 28.6%.
Oh, 0. Oh, yeah, okay, sorry.
Okay? Questions on that? Can probability ever be over 100%? No. Can never be over 100%. The best you can do is that every single event that can happen, you deem to be a successful event. So if there are 500,000 possibilities, and you decide that every one of those possibilities is a win, then your probability is 500,000 over 500,000, which is 1 or 100%. Okay, now, I'm just trying to not erase that. How many of you guys are using this at all? Nobody? Okay, so I can erase this whole thing then? Okay.
Sure. Can I ask you a question?
B, simultaneously. Randomly drawing, 2 candies, 1 after, other, no.
Simultaneously.
Yeah. Simultaneously. And getting to green. So now we have the same definition. Sorry, rather we have a slightly different definition for the successful event. We have the same formula. Now you are literally going in and grabbing 2 green at the same time, not one after the other. So literally imagine that your hand is physically capable of just going in and taking 2 at once. Darwin, how many ways can you go in there, given the fact that there are 4 greens, and take exactly 2 of them? If you're taking them at the same time, you don't care about the order in which you take them. You're going in, you got to get exactly 2 green. And they're not coming one after the other. So you have 4 successful items from which to choose from, and how many are you choosing? So you have 4, choose 2. Okay. So now, you know what, I'll even write it as C. I'll write it as C to make. And then Darwin, how many objects do you have total?
7.
Okay, and you're not taking them one after the other. And your percentage comes out to 28.6%.
0.57.
Which is 0.6.
Sorry.
Okay, so you see the probabilities are the same, the theoretical probabilities are the same, and you can see why. Because this is equal to 4p2 divided by r factorial, right? And this is equal to 7p2 divided by r factorial, or in our case it's not r, it's 2 factorial, right? Okay? And when you have division, this goes up, right? You multiply by the reciprocal of the denominator, remember? You change division to multiplication, this flips around. The 2 factorials go. Okay? So it turns out that these 2 physically different or mechanically different processes, turns out that they yield the same probability. Are they physically different experiments? Yes, they are. They are physically different experiments. If you have a machine that goes in and grabs 2 objects at once versus one after the other, they're different. Now, Alexei's smart, because Alexei, and that's, I mean, I remember when I first thought about this stuff, I was thinking about the same way. He's thinking on the margins, he's like, well, really, can you ever have something grab 2 things exactly at the same time? Isn't there always a slight time differential, and therefore you can apply that limiting logic and say that they're effectively equivalent. Okay? But you don't need to. you can imagine a theoretical machine that does grab the two objects at the same time. In which case, that would be the appropriate combinatorial logic, and in which case you get 28.6, and in this case you still have 28.6. Right? Just curious. No, good. Now, should we do it empirically? Okay, let's do it empirically. So we need somebody to sit here. I guess for effect, since you guys are filming it today. Here, well, Yanjun will be the director. General, okay, who wants to do this? We need somebody to sit right here. Who wants to sit here? Okay, Aaron, let's go. So Aaron, your job each time. Your job each time is to go in there randomly, not look, like shake the box out. And since we all agree that it doesn't matter whether he takes one at a time, doesn't matter, right?
We're doing it 17 minutes late.
What did we just say? Well, actually, you're right. Technically, we haven't proven it empirically. Whatever. It doesn't matter whether you take them at the same time or if you take them one after the other. So you take two and we see what we got. What did you get? And all we have to do is we just have to mark success or failure. Okay, what did he get? Did he succeeded. So we're going to say yes. Next, go throw them back in. You got to do this fast. Stir. Throw. But don't break them. They're not mine. Success or failure?
Fail.
Go. You don't have to shake them so.
Failure.
Oh, we're going to need a lot of data points.
Keep building. Failure.
Fail.
Failure.
Fail.
There's going to be a lot.
Failure.
Failure.
No.
Failure.
Oh! Fail. Fail.
Failure. Failure. Failure.
Fail.
Oh, you got two oranges then.
Oh, that's still a failure.
Oh! Fail.
Two greens.
We're falling off here. But it's okay. We have so few data points.
Still fails.
Fail.
Wow. We might have to.
How many
What the hell are you drawing? Are you? Okay, you know what? I want Kate to take over. Kate, your turn. You're jinxing this thing. Just give her the whole block.
Bad luck.
Go ahead.
Fail.
So much for theoretical probability.
Fail.
So how many points do we need? Like,
The more points you need, the more points you have, the better.
I'm gonna go through it or?
Fail.
Oh, I don't like the way this is going, so we gotta keep going. Okay, I'll do this.
It wasn't my fault.
Someone check mark.
You need a check mark.
Sir, you have bias.
I'll do it. I'll do it, sir.
You shouldn't do it, sir.
Go ahead. You watch me, tell me if I'm cheating.
Fail.
Where? It doesn't count. That doesn't count.
Fail.
Fail.
Are there really 4 in there?
Fail. Fail. Fail.
No worries, so we're giving that like an hour.
Fail.
Okay, something's up with these double orange.
We got more oranges than greens.
Are they poofier, the double orange? They are poofier.
Fail.
Oh, I can already tell. It's always double orange.
Why?
I know why. This is actually fascinating. This is great. I have an idea. I can already cheat though now. Watch. Watch.
Okay.
Watch.
You're
You're
searching
taking
for
more
that.
time. You're taking more time. Stop there.
What does that tell you?
You cheated.
You cheated.
No, but it tells you they're not all the same. What does it tell you in terms of the definition? That the ones the ones that the orange ones that are in there they're easier to grab, like they're bigger. Like these ones are flatter. Feel that. And now feel that. You see it? See what I mean? That's interesting. So these things suck. But now it's cheating. Now it's cheating. I know. Like watch. I'll do
So
it.
let someone else do it then.
I'll do
You
it
shouldn't
again.
take that much time. You're taking too much time.
We gotta go again. We need to use something that's better.
Sir, give it to someone else now.
We need stuff that's the same.
Sure, what about draw a smiley face?
Wait. Okay, wait. I got it. I got it. Okay, this is good. How many oranges are supposed to be in there? 2. Okay, these are good. This is fun. Okay, I got the orange are good. I need non-poofy green ones. That have the same feel. That's fine.
So why don't we, instead of touching it, we try to like drop them out of the
No, but it
What about more some
You can
table
change the
tennis
colors,
balls?
like for blue.
That's gonna be more fair than touching it.
This is great. Okay, yeah, that's pretty good. Okay, ready?
Yeah.
Start again. No, erase the whole thing. 1x. Go, erase the whole thing.
Sure. Fail. Fail.
Okay.
No. Fail. 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 No. That one doesn't count. Oh, finally. Fail.
It's gonna take a while. We're gonna get like 50
Fail.
data points.
Fail. 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 Oh, yeah.
Doesn't count.
So you
看这张画你的课完。
So you're taking more time.
I'm trying to go as fast as I can. It's hard. Because they're all flapping together.
So we should give a name to the video. Segev.
Oh shit.
Fail. Fail. Fail.
How the hell does that always happen?
What? How can you grab that?
It's the same. I'm telling you, it's these poofy orange ones. Doesn't make sense.
That's what I'm saying, so you can't. You
No.
shouldn't touch it.
Milad, don't tell me anything. You're sitting back in the corner. Ever since that proof, you've lost all credibility. Zero. You have none. It's over. So much for theoretical probability. Are they actually mixing?
Fail.
That's the better way to do it.
Fail.
So can we keep the green ones and the orange ones? Because the chance will be easier.
It would be interesting to see.
Get more points.
那他换了一个课，我操！
Okay, somebody want to keep a rally? How many data points do we have so far?
4, 5.
So I need somebody to, because somebody's got to be doing division, right? So somebody's got to do, it's got to be successes over total. Successes over total. How many successes do we have so far?
5.
So far it's 15%.
Or 15%. Now the thing is, the more data points you go, the harder it is to change the data. But ideally what you want to see is a flat line at around 28.6, right? Which it doesn't seem to be.
But I think you have to use computer instead of handshaking it.
No, you don't. What I did last year was I had like groups, like 7 groups, and every group did it a lot, and then I took all of the data from all the groups.
You plus them together.
Yeah, I just add them, I put them all together. And then the data flatlines. We'll see. We're losing though. I think it's the experimental design.
And someone consumes one of them.
Now, that would be an interesting study to figure out why my design is flawed.
Because you're touching.
But I'm not thinking at all. I'm just,
You're not thinking, but it's easier to grab the other one.
right, and the question is why?
Because it's the size of it.
But they look pretty much the same size.
But they're not.
But
They're
they
not
may
the
weigh
same.
different.
What?
They may different weight.
May is not a good answer. So this is not working.
So why don't you just like try to drop them?
Huh?
Like shake and drop like two without touching it. How would you drop it down?
That's the most ridiculous thing I've ever heard.
It's gonna take time, but like.
Yeah, but how would you exactly drop to? You know, drop to the other, that's
That is
Yeah,
silly.
they try, but then that.
Oh.
After 50 tries, you got like 2. Or 2 now.
Somebody should keep track of the orange, the double.
Sir, I think you should stop doing that, otherwise you'll go insane.
No, we'll do a few more. I've already gone insane.
I think if you have one more double orange, you will go insane. Okay, go insane.
How can that be? You just keep track.
Okay.
Fail. Let me check.
So you have 3 in your hand, that doesn't count. It's cheating.
I'm not cheating, I'm not thinking.
You have
This is
to
like
really drop it.
17.6%.
And now what? You need a spreadsheet is what we need, right? That's the problem. You need Excel or a graphing calculator. Oh!
18.8. 20.
We're at 20 now. Fail.
So you really want to make it
Yeah.
28? Fail.
What is so special about you?
Sir, consume it.
This is interesting. How many are in here and how many are in there? Do they feel the same? Fascinating. Yeah?
Yeah, because you don't have one here.
We don't have a lot of data though. That's the thing. We don't have a lot of data. Give me 5 more minutes and then I'm quitting.
5 minutes sleep, guys.
Fail.
Alexei, we just had another success. Let me make sure. Wait, are they getting stuck under here? Wait a minute. Hang on. There are only 3 green in here. That's good. Calculate the probability for 3 green. What the hell happened to the other green? Okay, hang on. We're not messing with our data here. Okay, so that's going to be, now our new is 3, it's 3 C2 over 7 C2.
14%.
6 C2, sir.
Sorry, over 6, yeah. What is that?
14%. 14.3.
14 point what?
0.3.
No, 6 C2.
Oh, it's
3.
6.
14.3.
What's 3 C2 over 6 C2?
20.
20%?
Yeah, exactly.
20%.
Oh shit, okay.
We're
what-
20.3%.
Now what are we at?
20.3.
You know, why did I lose one before?
We're
Did it
going
sneak?
higher.
Oh, it's over there.
What?
I think it's behind there.
Whatever. No, that's the blue one. You know what? And I'm not going to use this stupid thing. I just need
Why
a.
don't you use a hat? Yeah. No, why not?
No, no.
You got exactly 20%, right?
What are we at so far?
20.3%.
Okay, ready? Eric, where are you going? Get up there. Get up there.
Your job's not done.
Okay, here we go. Also, you guys want to see. Fail.
We should add some music to it. Shake it, shake
Fail.
it, shake it, shake it.
Fail. Well, you guys can see.
Fail.
Win.
Oh, yeah. Fail.
Fail. So it's about 1 in 5, right?
Fail. Fail. Fail.
Alexei, you on this stuff? Are you on this? You're on it?
Fail.
Now, I'm not looking at the process. Yanjun, are you looking at the process? Does it look right? Is everything moving around? Threaded double orange. What percentage are we at?
I miscounted.
No, that doesn't. Hard. Win. See how cute Janice is? Every time double green comes up, she goes. See, she's cheering for me. Oh.
Okay.
Yeah, I was good.
Fail.
You only want to point out my failures. Why don't you want to point out my success? It doesn't matter, because eventually, as the gods settle things out, it's gonna flatline. What are we at so far, folks? Win.
Oh.
Does anybody have an iPhone with a spreadsheet? Because then all you have to do, you know what I'm saying? Whatever. Fail. Come on, Eric, faster.
Fail.
Wow, we're more than 50 points.
Are you on this?
Fail.
Alexa, where are we at?
Fail.
Oh, you called out fail? You want to talk about bias, experimental bias?
Fail.
Okay, what percentage are we at so far?
Fail.
Success.
Oh,
I'm good.
Go to Vegas with some pink eye. Oh! Double oranges split places with double green.
Did you change something now?
No, but honestly, before that was interesting. The oranges that were in there were poofier. What does that tell you about experimental design? It's crucial, right? So is the okay. What are we at?
I can't calculate on the stop.
Okay. But you can't. Oh shoot. Okay. Who has? Do I need to get my bloody thing?
Yeah.
Yeah? I'll get my laptop? Okay, fine. Pause. It gets harder and harder
You don't need
to
a
move the dots. No, we don't need it. And why does it get harder and harder to move the dots off of the line with time? Did you want? What? Yeah, because each one of these data points is a function of what just happened and everything that came before. So you can think of it as kind of like if you have a bathtub and you start filling it in with drops of color. So let's say you start filling with blue drops. You put in 2 blue drops and then you put in a red drop. It's going to go a little red, right? Now imagine a bathtub full of 10,000 blue drops. You put in a red drop. Is it going to change the color of the bathtub? No. So this thing is going to get harder and harder to pull away, and eventually it's going to flatline at 20%. We got that too, right? That's important that they see that. Okay, so mission accomplished as far as that, right? Right? You guys get the idea? Okay, so take a couple seconds. Let me put this stuff back before she kills me.
And you're watching it they're supposed to understand.
Sorry?
Arguing for-
Oh yeah, we'll just do arguing of the quizzes. Where did I take this from?
Yeah.